So in our first two videos, we've set the scene for understanding how light interacts with solids. Now we're going to start into classical electromagnetic theory of solids. And this is going to take a couple of different videos. So I want you to consider a solid, an electric field. This isn't actually a solid, this is just showing a molecule, but here you can see this is hydrogen chloride. The hydrogen end of the molecule is positive and the chlorine end is negative. So it's just got a little bit of charge distribution where it's slightly more negative at one end and slightly more positive at the other. If there's no electric field applied, then these molecules can be oriented in any direction. But once you switch on a field, they will tend to be oriented so that the negative end of the pole points towards a positive charge or points in the direction of the field. How does a solid material respond to an electric field? Well, charged particles are going to move in an electric field as we just described. When you have a dielectric medium, not a conductor, the electrons are attached to their atoms and the electrons can move. They're going to oscillate around the atomic nucleus. They're going to be affected by the electric field, but they're not going to move very far from the atom. But you are going to get some polarization. Whereas if you have a metal, the electrons are not bound to the nuclei of the atoms. And so you'll get a different reaction with a metal compared to a dielectric material. Either way, we have charged particles and the charge on a particle is Q. And in an electric field of value E, we will get a force on that charge of F equals to QE. And so what we get is that our atoms or molecules or bits of solid will become polarized because the electric field is putting a force onto the electrons in one direction and the nucleus in the other direction. And so they will be offset from an equilibrium position. Okay, so as we just said, atoms and molecules are basically made up of electrical charges. You've basically got electrons and an ion or a nucleus. And they're going to oscillate around, and that's going to depend on their specific masses. So you're going to have a natural frequency that the atoms, the electrons and the ions oscillate relative to each other. But when we put them into an electric field that has a frequency nu, then the oscillator, the oscillation of the atom is going to be forced to vibrate in the same frequency as that radiation. That is, the electric field is now forcing the atom to vibrate in a certain way that is not necessarily the same as its natural frequency. So let's talk about what happens when you have a natural frequency. So here, this is with sound waves, but it works with electromagnetic waves too. I'm sure you're all familiar with this idea of resonance. What this is showing you is that if you have a tuning fork and it has the same frequency, that by hitting that tuning fork, you're sending out sound waves that are the same as the natural frequency as the other tuning fork. And so what happens is that tuning fork begins to vibrate in the same way. That is a resonant effect. If the two tuning forks were different frequencies, you would not see that ping pong ball bounce. You would not get the same reaction because it wouldn't be vibrating in resonance. So just like that, when we have an atom or a molecule in an electric field, now what happens is if the electric field's frequency is very different than the natural frequency of oscillation for that atom or molecule, then the amplitude is going to be small. You're going to have a little bit of forcing of motion, but it's not going to be a huge vibration. But if it's close to the natural frequency, then we start to get a resonance. So now as you get the frequency of the light is getting close to the natural frequency of the atom or molecule, then you're going to get a huge amount of motion within that vibration of the atom or molecule. So here what you're seeing is an electric field, and I've got a charge and it's moving up and down. And so you can think of this as being, this is the reaction of, say, an electron that is in an atom, and it's moving up and down from one end of an atom to the other as the electric field is going up and down. And the way that we think about this in terms of how light is being absorbed is that as the electron moves up and down, or the molecule is wiggling in other ways. We'll get into that later. As the electron is moving up and down, there must be some sort of friction that has to be overcome, and that frictional force is proportional to the velocity. So the electron is moving fast, and it slows down as it gets to the top, and then it comes back down. And so what we get is that frictional force means that some of the light gets absorbed in order to get that motion working. When we have small amplitudes of forced oscillation, that is, when the frequency of light is a long way from the natural frequency, then the frictional force is just going to be very small and there's virtually no absorption. But as we get close to the resonance, as we get close to the natural frequency of the atom, you're going to have a really big amplitude of forced vibration, and you're going to get a much bigger frictional force, and so that means that more absorption happens. When we're close to the natural frequency, the nu naught, the amplitude of oscillation is so big, and that means that we have a large frictional force to overcome, and that gives rise to an absorption. We get radiation near the natural frequency of the oscillator will give rise to an absorption band. So if you've got something that is naturally oscillating like this, it will give you an absorption of radiation at that wavelength or frequency. So let's get into the Lorentz model. What Lorentz postulated was that you could model the binding force between two atoms or two molecules as being a spring. So think of this as being, you've now got a solid and you've got to stick your molecules together, and so they're stuck together by springs. And that spring would behave as we expect a spring to and obey Hooke's law, so that we have a restoring force that relates to the spring constant. So this eta here is the spring constant. I know we normally use the letter K, but in a previous video, I went into why the letter K is evil and that we should not use it for anything. So I'm using the letter eta here to try to avoid too much confusion. We've got springs that are holding our molecules together, and when we have a solid, we have a whole system of springs where all of the masses are stuck together with springs. So here this is kind of shown just doing it for an atomic nucleus, but this works for any system of particles stuck together. So it can be intermolecular as well as intraatomic. So here I've got an atom here. There is no electric field applied, and so the spring is not stretched out. But now I've got the electric field is applied. The electrons are now displaced relative to the nucleus. They're more stretched out in this direction. And so we get this spring that is now a displaced mass, and we will have a restoring force on it that is to do with the spring constant. So if we've got an oscillating electric field, now what we're going to get is the electrons are pulled in one direction, and then the other, and then they're pulled back again, and then the other. And so our electrons are now moving in a harmonic motion. They're going back and forth as the electromagnetic wave passes through, as the electric field goes up and down. We basically can ignore the magnetic field. It doesn't have much of an effect, especially compared to the electric field. And so what we get is we're going to have some motion, but we're also going to have a friction, which we can model as a damping force. So basically, the spring has a natural damping, and so we're going to get some friction that occurs that gives rise to an absorption. So let's consider this nice, simple, one-dimensional rudimentary lattice. Each one of these is an atom or molecule. They are separated by a distance a, and this one here, this is the nth particle, and it's going to be displaced in that direction by a distance delta n. So my nth atom is displaced by a distance delta n, and it's parallel to the chain of atoms. My nth plus 1, that would be this one, and nth minus 1, that's this one, are also displaced by delta n minus 1 and delta n plus 1. But what that means is that if this one has been displaced and this one has been displaced, the actual displacement relative to its neighbors is now delta n minus 1, because that one has moved a bit, and delta n plus 1 minus delta n, because that one's moved a little bit. our displacement relative to our displacement of our nth particle depends on the displacement of the other particles. According to Hooke's law, there's going to be a restoring force. This is its equilibrium position. When it is displaced, it's going to have a restoring force that tries to pull it back to its equilibrium position. And that restoring force is given by Hooke's law. So that's the minus e to x, where in this case, x is our displacement. Our nth atom is experiencing a force F given by Hooke's law, and it's connected by two springs. We've got a spring connecting it to n+1 and n-1. And so what we get is a restoring force, which is, this is the spring constant, this is one spring, and this is the other spring. And they're acting in opposite directions, so it's one minus the other. And so we can then put it together like this, and we get this equation for the force that is acting on this particle. But we can also talk about the acceleration of this particle, because it's being pulled this way, it's being pulled this way. And so the acceleration it's going to feel is just F equals ma, which in this case is given by the displacement dn. So it's d squared n over dt squared. And so what I can do is now put this together. The acceleration that my particle is going to feel is due to the two springs that are pulling it. And that is my Hooke's law. And so I've just equated these two things. So this is the equation we just came up with. This is my F equals ma. This is my Hooke's law. And all I've done here is to divide out by the mass. So I've got the acceleration on one side, and I've got the spring constant and the mass on the other, and then this is the displacements. An equation like this is basically a wave equation, and it's going to have a solution that looks something like this. In this case, what we have is the A is the distance here that you can see here. So we've got, this is the wave number. I'm using kappa here because, again, K is a problem, and we will need to use K in a future video in this format. So I'm using kappa as the wave number. I should have used something else, but I couldn't figure out what to use. And then omega is the angular frequency, and delta zero is the amplitude of the oscillation. So this is just a wave. And this kappa is the wave number, so it's just 2 pi over lambda. This is my solution, and this is my original wave equation. And so I'm going to plug this dn into here. So I've got d of n is just putting an n in here, but that means that d of n plus 1, sorry, n minus 1 here, I put in n minus 1 here, and d of n plus 1 here is in here. The acceleration now is given by this equation, where I can now do some simplification here. I'm just doing some math. So all I've done is to substitute in the delta zero ei kappa na minus omega t. And now I'm taking this one and I'm reorganizing it a little bit. So I've just basically multiplied this out. So I've got kappa na minus kappa a, and I've got kappa na plus kappa a. And now as I rearrange that some more, all of this ei kappa na minus omega t, that's common to all of these. So I can pull that out of the bracket. And so now I've got this equation that gives me back my my delta n equation, and I have this exponent piece here. I'm going to dig into that next. So this is the equation we just came up with, but this is basically the same as the function in terms of exponents of a cosine function. So cosine theta equals a half of e to the minus I theta plus e to the I theta. So here I plugged this back in. I've got my acceleration, and I've plugged in now this cos piece in here. So I put in 1 minus cos theta in here. There's a 2 here. I made that into a 1 and those into halves. So that gives me that half, and so on. Here I have my equation for the displacement of the nth atom. And you can see that's the same as this thing here, this thing here. And this is basically a wave equation. So this is how I've got a frequency, a displacement, and an acceleration. And if I bring all of these three together, I've basically got rid of that thing and turned it into a delta n. And then I've taken that delta n and put it over here so that I've rearranged things to get an equation for the frequency. So what I've got here now is that for a given atom, I have an equation for the frequency of its response to an electric field based on this spring recoil action. So now let's do a little bit more math. So this is just a trigonometric function that the cos of 2 theta is cos squared theta minus sine squared theta. And remember that cos squared theta plus sine squared theta equals 1. So I can do a little bit of rearranging in here, and I can get something that tells me that 1 minus cos 2 theta is sine squared of theta. Well, I've got a 1 minus cos theta up here, so I'm going to have to put in a half here to make up for the fact that this is 2 theta. But that's all I've done here. So now I've got that my angular frequency is given by this equation. And since it's omega squared, I have to square root it. So I've got a term that is the spring constant, which relates to the bonds between the atoms, the masses of the atoms. We've got the distance between the atoms. This is something that is unique to a given substance. And what this tells us is that there are certain vibrational modes that are allowed in the lattice. Now, in this case, what we get is what's called acoustic modes. We cannot have frequencies higher than a certain number. Basically, we can't have them higher. Remember that, sine of something has to be between +1 and -1. We basically cannot have a frequency higher than this eta over m. And so that tells us that we have a certain range in which we can have these acoustic modes. That's a fairly simple case, but now we're going to consider what happens when we have two different atoms in our chain. So we've just been through the process of figuring this out for a simple thing where we have the same atoms all the way across. Now we're going to have two different types of atoms, or they could be molecules. We've got particles X and Y. The nth particle, this one again, is of type X and is displaced by dn. As before, the nearest neighbors are going to be displaced by n-1 and n+1, delta thereof, but those are both the y's. So then we also need to account for the next ones out. So now we've got, this is delta of n-2 and delta of n+2, because they're the next x's. We need two different equations to get the restoring forces, because it's going to be different for the atoms of type X compared to the atoms of type Y. What we find is that, again, just applying what we did before, where we've got a displacement of the atoms, we've got the f of X is just like it was before, but now f of Y is the next one along. So now we've got delta n minus delta n+1, and now it's the next piece across, which is the n+1 and n+2. So that brings us to the concept of optical and acoustic modes. So we already talked about acoustic modes for a single type of particle in a chain. Now, if we followed that same procedure as we did before, but without going through all the tedious math on screen, we end up with omega squared is equal to this equation here. And what we get is that a term that is related to the mass of the X atom, the mass of the Y atom, the distance between them, and also their spring constant. But otherwise, it's basically the same. Now, if we take this where we have the minus sign in here, then we get a maximum angular frequency. So this is, again, that same maximum frequency. This is that acoustic mode. That same thing that we looked at before, you cannot get a frequency higher than this for the acoustic mode. But we can also take where this is a positive sign, and then we end up with two different frequencies. One is going to be basically the equivalent of that acoustic mode, but is now for the Y particle mass. And then the other is a maximum, which is where you're taking into account both the Y and the X. What these frequencies actually give rise to is you can have a frequency, anything, you can have anything between this frequency and this frequency. And so you can't have vibrations in between. And so what this is telling you is basically what we did is we put our particles into an electric field, we displaced them, and then we said it's going to be restored by this spring force. And now by just following through on that, what we get is that we have a onset and cutoff for an absorption band. That is, this is the range within which there will be an absorption for a given material. So it depends on the spring constant, which obviously depends on the material itself, and on the masses of the material, of the pieces that make up the material. There is, in fact, a forbidden space between that minimum, which is where this was the omega A, which is the acoustic mode, and this optical mode. And so basically, this is the range that we really care about for what is going to be really well excited by light and the electric field of light. Okay, so in this section, we basically have taken the idea that there is a restoring force that comes from a spring that constitutes the bonds between two atoms. And as a particle is displaced by an electric field, there's going to be an acceleration of those particles as the spring tries to pull it back into place. And that allowed us to derive equations for the optical and acoustic modes. So these are the frequencies where the lattice can actually absorb, and they're based on the spring constant and the masses of the particles involved. But this basically shows you how this Lorentz model, this idea of springs holding your atoms together, allows you to come up with a model for how light is being absorbed. In our next video, we'll apply this to actually putting an electric field in place.